A famous athlete once said, "Life is like a swimming pool. You dive into the water, but you can't see how alkalonic it is." Er, uh, did he say you can't see how deep it is? Anyway, we're headed to the water fun park. And yes, that's fun with a pH, where we'll look at simple acid-base disorders and their compensatory responses. We'll drop by the lemonade stand to discuss metabolic and respiratory acidosis, then go poolside to dip into the basics of metabolic and respiratory alkalosis. But first, let's test the waters by looking at normal values for blood pH, plasma bicarbonate, and partial pressure of carbon dioxide. Under normal physiologic conditions, the lungs and kidneys do a great job of maintaining the pH of blood within a normal range of 7.35 to 7.45. And it just so happens that the normal pool hours here at the park are 7:35 to 7:45. Oddly specific, but it gets the point across. Looks like the day started way too early for this snoozing ticket clerk. He's catching some serious open-mouthed disease while cozied up next to a box of baking soda, our recurring symbol for bicarbonate, to help you remember that the normal range for plasma bicarbonate is 22 to 28 milliequivalents per liter. As for arterial PCO2, 33 to 45 millimeters of mercury is normal. Definitely more normal than this smoking swim instructor holding a free class flyer. And when we say smoking, we mean literally smoking, because smoke is our recurring symbol for carbon dioxide, though nothing against our scantily clad friend here. Now, let's dip our toes in and talk about acidosis and alkalosis. Acidosis, symbolized by this acid-rich lemonade stand, is characterized by an increase in the hydrogen ion concentration in blood, which is why we've marked up the stand with these plus sign lemons. Alkalosis, which we've symbolized by this dark blue alkaline pool, is characterized by a decrease in the hydrogen ion concentration in blood. And see, not a single plus lemon over on the pool side of the park. Abnormalities in the blood pH can further be categorized as metabolic, caused by a primary disturbance in the bicarbonate concentration, or respiratory, a primary disturbance in PCO2. Don't worry, we'll get into both of these soon. But first, to get a better understanding of the relationship between pH, bicarbonate, and carbon dioxide, let's review the Henderson-Hasselbalch equation. This equation states that pH equals 6.1, the dissociation constant of carbonic acid, plus the log of the plasma bicarbonate concentration divided by 0.03, the solubility coefficient for CO2 in blood, times the partial pressure of arterial carbon dioxide. The important takeaway here is that pH is determined by the ratio of plasma bicarbonate to CO2. Let me show you what I mean. This rainbow gradient should remind you of the pH scale. If you recall, CO2 is a Lewis acid, so a higher concentration of CO2 makes the blood more acidic. That's why our smoker is standing on the acidic end of this rainbow pH scale. On the other hand, bicarbonate is a weak base, so higher concentrations of it make the blood more alkaline, which you can remember with this box of baking soda on the alkaline end of the pH scale. All right, now that we've covered the normal values for PCO2 and bicarbonate, and how they work together to keep blood pH balanced, let's move on to the acid-base disorders and the compensatory mechanisms that occur to get blood pH back into normal range. To start, let's head over to this lemonade stand and these kidney-shaped inner tubes, our symbol for metabolic, to talk about, you guessed it, metabolic acidosis. Metabolic acidosis is characterized by a low blood pH due to a fall in serum bicarbonate concentration, which is why there's a box of baking soda falling off this lemonade stand. To try to bring pH back into normal range, the respiratory system compensates for metabolic acidosis by increasing ventilation. Faster and deeper breaths mean more acidic CO2 can be removed during respiration, which reduces the arterial PCO2, thus raising blood pH. This is represented here by this big gusty fan, which, in addition to drying off this little guy, has blown out this tiki torch, leaving behind a teeny tiny little wisp of smoke. I guess that's one way to dry off at the water park. There are many causes of metabolic acidosis, which can be narrowed down by evaluating the amount of measured serum anions relative to measured serum cations. Depending on the difference between cations and anions, metabolic acidosis can be categorized as anion gap or non-anion gap. We get into this in way more detail in the metabolic acidosis sketch, so be sure to check that out. Next up, let's drop in on this grill master who's wearing a lung-shaped life vest, our symbol for respiratory, to talk about respiratory acidosis. In respiratory acidosis, blood pH decreases when the lungs can't remove enough CO2 due to hypoventilation, which is why this poorly ventilated lemonade stand is accumulating so much CO2 smoke. Jeez, who starts grilling without plugging in the fan? Oh boy. To try and compensate for this respiratory acidosis, renal reabsorption of bicarbonate increases and excretion of bicarb decreases to keep more bicarbonate in the body, thus increasing blood pH. This explains why such a large crate of baking soda has been delivered to our smoked out lemonade stand. Just in the nick of time. Now, let's sit back in a kidney-shaped inner tube and float on to higher blood pHs, starting with metabolic alkalosis. In metabolic alkalosis, blood pH is elevated due to an increased bicarbonate concentration, which is why we have this rather large, raised-up box of baking soda being poured into the pool. To try and compensate for metabolic alkalosis, the respiratory system responds by decreasing ventilation, which raises the partial pressure of CO2, since less is being expelled through respiration. And more CO2 in the blood means a lower pH. This is why this lifeguard's personal fan is on the fritz and filling his station with smoke. Help? This lifeguard needs a lifeguard? We've finally reached the final acid-base disorder in this sketch. Respiratory alkalosis. Then we have our lung-vested birthday boy here to help us celebrate. In respiratory alkalosis, blood pH increases due to hyperventilation, which causes too much CO2 to be expelled during respiration. That's why this big fan has just taken the fire out of this birthday candle, leaving behind only a tiny little wisp of smoke and some broken dreams and wishes. Sorry, kid. Well, to make up for that, the body gets rid of bicarbonate by decreasing renal reabsorption of it, or increases its excretion, leading to a lower blood pH. Decreased bicarb is symbolized here by this flattened, discarded box of baking soda. And basically, that does it for acid-base disorder basics. Before we towel off, let's backstroke through the pool one more time and review some key points. The normal range for blood pH is 7.35 to 7.45. The range for normal serum bicarbonate is 22 to 28 milliequivalents per liter, and normal arterial PCO2 ranges from 33 to 45 millimeters of mercury. Acidosis refers to an increase in the hydrogen ion concentration, while alkalosis refers to a decrease in the hydrogen ion concentration. Based on the Henderson-Hasselbalch equation, pH is determined by the ratio of plasma bicarbonate to CO2. pH varies inversely with the partial pressure of CO2 and directly with the plasma bicarbonate concentration. Then we covered the 4 acid-base disorders and their compensatory mechanisms. In metabolic acidosis, blood pH is too low due to a decreased serum bicarbonate concentration, and its compensatory response is hyperventilation, which decreases the PCO2. Then we went over respiratory acidosis, which is characterized by a low blood pH due to increased PCO2 caused by hypoventilation. Respiratory acidosis is compensated for by holding on to more plasma bicarbonate, either through increased renal reabsorption or decreased renal excretion. Then we went poolside to check out the alkanes, starting with metabolic alkalosis. Metabolic alkalosis is caused by an increased bicarbonate concentration that raises the pH, and is compensated for by an increase in the PCO2 via hypoventilation. Last, respiratory alkalosis is a high blood pH caused by decreased PCO2 due to hyperventilation, and is compensated for by decreasing the plasma bicarbonate concentration. Before we go, you should know that the 4 acid-base disorders we just covered are simple acid-base disorders. Simple means that only one acid-base disorder is present. When an acid-base disorder is described as mixed, that means that more than one acid-base disorder is occurring simultaneously. An example of a mixed acid disorder might be someone with emphysema that is suffering from food poisoning. The emphysema causes CO2 retention, which you know as respiratory acidosis, while the vomiting from food poisoning causes a second disorder of excessive proton loss, or metabolic alkalosis. One last thing. As we detailed throughout this sketch, abnormal blood pH caused by a disturbance in either the metabolic or respiratory components can be partially compensated for by a change in the other component. For example, a high respiratory CO2 can be compensated for by increased bicarbonate via the kidneys. In a simple acid-base disorder, the values for pH, bicarbonate, and CO2 can be predicted using some general rules called renal rules that are based on expected compensatory changes. In general, if a patient's actual blood values are equal to the predicted values, a single acid-base disorder is present. If the patient's blood values are different from the predicted values, a mixed acid-base disorder is present. Well, that about does it for acid-base disorder basics. Now, if you'll excuse me, I'm going to go see if I can't cheer up that birthday boy. Happy sketchy birthday, Timmy, happy sketchy birthday. This is a terrible song. You're on your own, Tim.